Tonight, we are going to walk all the way to the edge of the universe and ask a question that sounds simple and turns out to be one of the strangest in modern cosmology. What is the edge actually made of? You have probably been told at some point that the universe has an edge. The textbook diagrams show it. A sphere of stars and galaxies with you near the middle, and a boundary out there somewhere, a horizon beyond which there is nothing, or beyond which there is something we cannot see. The image is comforting in a way. It gives the cosmos a shape. It makes the cosmos finite, contained, knowable. The image is also misleading in 5 separate ways, each of which is its own answer to tonight's question. Tonight we're going to take those 5 answers seriously, one at a time. We are going to discover that the word edge means something different in each one. We are going to find out that the edge of the universe is not a wall, not a fence, not a line drawn anywhere in space. It is, depending on which kind of edge you mean, made of light, made of expansion, made of darkness, made of the first stars in cosmic history, or made of something so far outside our current physics that no honest scientist will tell you they know what it is. Before we get started, sit for a moment with the strangeness of the question itself. When you ask what something is made of, you usually expect an answer in terms of materials. A wall is made of brick, an ocean is made of water, a star is made of plasma. Materials are the things you can hold and weigh. The edge of the universe, by contrast, is not the kind of thing you can hold. It is a property of geometry, light, time, and the history of expansion. The edge is made of relationships, not substances. And yet, when you ask carefully enough, each of the 5 edges turns out to have a real material answer. The CMB has a temperature and a composition. The event horizon has a physical structure. The cosmic dawn was briefly made of stars and hydrogen and a kind of fog that has now lifted. Each edge has its own answer. Tonight, we're going to walk through the 5 answers slowly. You can sleep at any point along the way. The story does not need to be finished tonight. It will be here whenever you come back to it. Pattern interrupt. The 5 edges are these. The first edge is the visible edge. It is the surface of last scattering, the place where the cosmic microwave background was emitted about 380,000 years after the Big Bang. The visible edge is made of plasma. It is made of light. It is the cosmic flash that surrounds us in every direction, dimmed by expansion into a faint microwave glow, but real and present and measurable in any radio receiver sensitive enough to feel it. The second edge is the reachable edge. It is the cosmic event horizon, the distance beyond which the expansion of the universe is so fast that no light leaving us today will ever reach the galaxies out there. The reachable edge is made of expansion itself. It is not a place. It is a property of the accelerating cosmos. It is the boundary between the part of the universe we can still touch, in principle, and the part that has already slipped beyond our reach forever. The third edge is the light edge. It is the particle horizon, the distance from which the most distant light has had time to reach us since the beginning of the universe. The light edge is made of darkness, or rather, made of the absence of light. It is the boundary beyond which we have not yet had enough cosmic time for any photon to cross. The light edge is made of what we have not yet been able to see. The fourth edge is the cosmic dawn edge. It is the era of the first stars, the time when the universe transitioned from a dark plasma fog into a sky lit by the first generations of luminous objects. The cosmic dawn edge is made of hydrogen and helium, and the first heavy elements forged inside the first stars. It is the chemical edge of the cosmos, the boundary between an entirely featureless early universe and the structured universe we now inhabit. The fifth edge is the theoretical edge. It is the boundary between what we can describe with the standard cosmological model and what lies beyond our current physical theories. The theoretical edge is, depending on which theorist you ask, made of inflation, made of a multiverse of bubble universes, made of something we have not yet imagined, or made of nothing we will ever be allowed to see. The theoretical edge is where physics runs out and speculation begins. 5 edges, 5 materials, 5 answers to tonight's question. Before we get started on the first edge, one more orientation. The deeper truth, the one that runs through all 5 edges, is that the universe does not have an edge in the sense most people first imagine. There is no wall, there is no fence. There is no place where the cosmos ends. The cosmos appears to extend indefinitely in every direction, at least as far as our best measurements can determine. What we call edges are not boundaries of the universe itself, but boundaries of our access to. The universe is, in the strongest sense modern cosmology can defend, much larger than the part we will ever observe. The edges we will explore tonight are the edges of our observation, not the edges of the cosmos. By the end of tonight, you're going to understand that this changes the question. The edge is not a place we could, in principle, drive to. The edge is a horizon in the strict mathematical sense. It moves as we move, recedes as we wait, expands as the cosmos expands. It is, in a sense, the universe's way of telling us that there is more out there than we will ever be able to reach. The edges are reminders of our finitude inside a larger thing. They're the boundary of what we can know. No one expects, when first asking what the edge of the universe is made of, that the answer involves 5 different horizons, each with its own physics. No one predicts that the most honest cosmological response will be that the question has been answered in 5 different ways across the past century. Absolutely no one anticipates that the simplest version of the question, "What is at the edge?" turns out to be a doorway into the deepest open problems in physics. Now let's begin with the first edge, the visible one, the CMB. The first edge of the universe is the surface of last scattering, and it is the brightest single feature in the cosmic sky, hidden in plain sight at a frequency just below the threshold of human vision. You cannot see it with your eyes. You cannot photograph it with an ordinary camera. But if you tune a sensitive radio receiver to a frequency of about 160 gigahertz, anywhere on Earth pointing in any direction you will hear it. A soft uniform glow, the same brightness in every direction, with the same characteristic temperature, the same spectral fingerprint. The glow has been called the most uniform thing in the cosmos. It is the cosmic microwave background. Take a moment to sit with what the CMB actually is. The CMB is light. It is light that left a particular surface in the cosmos about 380,000 years after the Big Bang, and that has been traveling across the expanding cosmos ever since, redshifted by the expansion from its original temperature of about 5,000 degrees Fahrenheit to a present-day temperature of about minus 455 degrees Fahrenheit, or just under 3 kelvins above absolute zero. The light has cooled, in cosmic terms, by a factor of about 1,000. It started as visible light with the color of an orange flame. It is now microwave radiation, invisible to the eye but loud in the radio spectrum. Walk with me through the moment of emission, because the moment is the key to understanding what the CMB is made of. In the early universe, before 380,000 years had passed since the Big Bang, the cosmos was hot and dense. It was hot enough that hydrogen atoms could not form. Every proton and every electron was free, moving independently through a plasma soup. The plasma was opaque to light, because every photon traveling through it would, after a very short distance, collide with a free electron and bounce off in a random direction. The cosmos was, in this era, like the inside of a thick fog. Light existed. Light could not travel. Then, as the universe expanded, the plasma cooled. At about 300 kelvins below the temperature of the surface of the Sun, the cosmos crossed a threshold. The electrons and the protons combined into neutral hydrogen atoms. The plasma fog cleared. Suddenly, the universe was transparent. Photons that had been bouncing around for hundreds of thousands of years could now travel freely. The first burst of light, released at the moment of recombination, has been traveling outward ever since. It is the CMB. It is the light from the moment the fog lifted. Pattern interrupt. The surface of last scattering, the place where the CMB was emitted, is not a physical wall, it is a moment in cosmic history. Every direction we look, we are looking back through time at the cosmos as it expanded outward from the Big Bang. When we look far enough away, we look far enough back in time to reach the moment of recombination. That moment, projected onto the sky in every direction around us, is the surface of last scattering. We are, in a real sense, sitting inside a spherical shell of light that was emitted 380,000 years after the universe began, and that has been propagating toward us across 13.8 billion years of cosmic time. What is the surface made of? At the moment of emission, it was made of hydrogen plasma at about 5,000 degrees Fahrenheit. The plasma was almost entirely hydrogen and helium, with traces of lithium and even smaller traces of beryllium and boron. No heavier elements existed yet. The first generation of stars had not formed. The cosmos was, at that moment, the simplest possible chemical environment, with just 3 or 4 elements in significant abundance, distributed almost perfectly uniformly throughout space. The light that traveled outward from that moment carries the imprint of the plasma's composition and temperature. Modern measurements, particularly by the Planck satellite operated by the European Space Agency between 2009 and 2013, have mapped the CMB to a precision of 1 part in a million. The Planck maps show tiny fluctuations in the temperature of the CMB across the sky, of order 1 part in 100,000, which encode information about the density variations in the early universe. From those fluctuations, cosmologists have extracted the values of the most fundamental parameters of cosmology: the Hubble constant, the total matter density, the dark matter density, the age of the universe, the geometry of space, all of it hidden in the patterns of slight warm and cold spots in the cosmic microwave background. No one expects, on first hearing about the CMB, that the most precise tool for measuring the structure of the cosmos would be a faint glow of light that was emitted before the first stars existed. No one predicts that the simplest and earliest thing in cosmic history would turn out to be the most informative. Absolutely no one anticipates the way the surface of last scattering, the visible edge of the universe, has become the single most studied object in cosmology, despite being not an object at all but a moment. By the end of tonight, you're going to understand that the visible edge is the closest thing the universe has to a true boundary. Beyond it, in time, lies the era when the cosmos was opaque, when light could not travel, when there was nothing for any observer to see, even in principle. The visible edge is the earliest moment of cosmic history that we can observe in the form of light. Before that moment, there is no light to be seen. There is only the inferred behavior of the plasma that filled the cosmos before recombination, deduced from physics rather than measured directly. Walk slowly through one more layer. The CMB is, at the moment we observe it, the most distant thing we can see in light. The galaxies we can see, even the most distant ones detected by JWST at redshifts over 13, are far closer to us in time than the surface of last scattering. The most distant galaxy is observed as it was a few 100 million years after the Big Bang. The CMB is observed as it was just 380,000 years after the Big Bang. The gap is enormous. Almost the entire luminous history of the cosmos sits between the CMB and the most distant galaxies. The CMB is the visible edge of an even older era, an era that produced the cosmic structure we live in today, but that was, in its emission, the simplest and most uniform state the cosmos has ever been in. Sit with this. The visible edge of the universe is hotter, brighter, and more uniform than anything we can see today. It is also, in its present observed form, the coldest light in the sky. It has cooled by expansion by a factor of about 1,000. The cosmic fire that gave birth to the light has long since faded. We see only the embers, red-shifted into the microwave spectrum, distributed uniformly in every direction around us. It is worth sitting with how the CMB was actually discovered. Because the discovery is one of the great accidental moments in 20th century physics, and the story illustrates how the visible edge of the cosmos went from a theoretical prediction to a measured fact in the span of a few decades. The theoretical prediction came first. In 1948, George Gamow, Ralph Alpher, and Robert Herman were working through the implications of a hot early universe. They calculated that, if the universe had begun in a hot, dense state and then expanded and cooled, the leftover radiation from the early hot phase should still be present today, redshifted into the microwave spectrum. They estimated the present-day temperature of this leftover radiation at around 5 kelvins. The prediction was published in the Physical Review and largely forgotten by the broader physics community. For 16 years, the prediction sat in the literature, occasionally referenced by cosmologists but not seriously pursued as an observational target. Then, in 1964, two radio astronomers at Bell Laboratories in Holmdel, New Jersey, were attempting to use a horn antenna for radio astronomy observations. The astronomers Arno Penzias and Robert Wilson had calibrated their instrument carefully and were trying to track down sources of unexplained noise in their measurements. The noise turned out to be persistent. It was not coming from any particular direction. It was not dependent on the time of day. It was not produced by any known source on Earth or in the solar system. Penzias and Wilson, after eliminating every other possibility, including the famous suggestion that pigeon droppings on the antenna might be contributing to the signal, concluded that they were detecting a uniform background of microwave radiation coming from every direction in the sky. While they were working through this, a team at nearby Princeton University, led by Robert Dick, was independently constructing an experiment to look for exactly the radiation that Gamow's group had predicted. Dick had reasoned, independently of Gamow, that a hot Big Bang should leave behind a microwave background, and he was building the detector to find it. When Dick learned that Penzias and Wilson had already detected the signal, he reportedly said to his collaborators something like, "Well, boys, we've been scooped." No one expects in the history of science that the most important cosmological discovery of the 20th century would be made by two radio astronomers who were not looking for it, while a competing team a few miles away was actively building the detector to find it. No one predicts that the discovery would happen by accident, through the elimination of instrumental noise. Absolutely no one anticipates the way the story of the CMB discovery became one of the great parables of how scientific progress actually unfolds. Penzias and Wilson received the Nobel Prize in Physics in 1978 for the discovery. The accidental detection was, at the time of the prize, recognized as the most direct evidence ever obtained for the Big Bang theory. The competing steady-state models, which had argued for a universe with no beginning, were essentially refuted by the existence of the CMB. The hot Big Bang became the standard model, in significant part because the CMB confirmed its most distinctive prediction, pattern interrupt. The temperature of the CMB, as measured by Penzias and Wilson, was about 3.5 kelvins, close to the Gamow prediction. Subsequent measurements refined this to 2.7 kelvins, the value we have today. The agreement between the theoretical prediction from 1948 and the experimental measurement from 1964 was strong, enough to convince almost the entire physics community that the universe had in fact begun in a hot, dense state. But the discovery was only the beginning of CMB science. Over the following decades, the CMB has been measured with progressively greater precision by a series of dedicated experiments, each one extracting more information from the visible edge of the cosmos. The first major space-based mission was COBE, the Cosmic Background Explorer, launched by NASA in 1989. COBE measured the spectrum of the CMB to extraordinary precision, confirming that it was an almost perfect blackbody, exactly as predicted by the hot Big Bang model. COBE also detected for the first time the tiny temperature variations across the CMB sky, on the order of 1 part in 100,000. The variations corresponded to the density fluctuations in the early universe that seeded the formation of structure. The COBE results earned George Smoot and John Mather the Nobel Prize in 2006. The next major mission was WMAP, the Wilkinson Microwave Anisotropy Probe, launched by NASA in 2001. WMAP measured the CMB temperature variations with much higher angular resolution and precision than COBE. The WMAP maps allowed cosmologists to extract precise values for the most important cosmological parameters. The age of the universe was determined to be 13.7 billion years, accurate to within about 100 million years. The Hubble constant was constrained. The total matter density and dark matter density were measured. The geometry of the universe was determined to be flat to within about 1%. WMAP was, in many ways, the experiment that confirmed the modern precision cosmology era. The most recent CMB satellite was Planck, operated by the European Space Agency from 2009 to 2013. Planck measured the CMB at much higher precision than WMAP, with finer angular resolution and more frequency channels. The Planck results, published in a series of major papers between 2013 and 2020, provided the most precise determinations of cosmological parameters ever obtained. The age of the universe was refined to 13.8 billion years. The Hubble constant from Planck was 67 kilometers per second per megaparsec, which would later become 1/2 of the famous Hubble tension. By the end of tonight, you're going to understand that the CMB has become, over the past 60 years, the most precise probe of cosmological physics ever developed. The visible edge of the cosmos is not just a faint glow we can detect. It is the most carefully studied surface in all of cosmology. Every parameter of the standard cosmological model has been extracted from the CMB data. Every alternative cosmology has been tested against the CMB constraints. The visible edge has become the gold standard for cosmological measurement. The next generation of CMB experiments is already in development. The Simons Observatory in Chile, currently coming online, will measure CMB polarization at higher precision than Planck. The CMB S4 experiment, a planned ground-based array, will push the polarization measurements even further. The proposed Lightbird satellite, which the Japanese Space Agency plans to launch in the 2030s, will measure large-scale CMB polarization patterns that could carry signatures of cosmic inflation itself. The visible edge, in this sense, is still revealing new information as the instruments improve. Few would anticipate, on first encountering the CMB in a textbook, that the most boring-looking glow in the cosmic sky would turn out to be the most information-rich surface in all of cosmology. Few of us anticipate that the most important measurements in modern cosmology are made by sitting and listening to a uniform microwave hiss for years on end in different frequency bands with extreme attention to detail. Almost nobody anticipates the way the visible edge, once it is mapped at high enough precision, becomes a complete dynamical readout of the entire early universe. The first edge is made of light. The light is hydrogen and helium plasma, frozen into a snapshot of the moment when the cosmos became transparent. The snapshot has been propagating outward ever since, expanding with the cosmos, cooling, fading, but never disappearing. The first edge is the most enduring feature of the cosmic sky. It is older than every star, every galaxy, every planet. It is the oldest light there is. The second edge of the universe is the strangest one to feel, because the second edge is not made of any material. It is made of expansion. Tonight, we're going to walk into the geometry of the cosmic event horizon. The event horizon in cosmology is the distance beyond which no signal we send today will ever reach the galaxies that are out there. It is the boundary between the part of the cosmos we can still touch, in principle, and the part that has already slipped beyond our reach forever, Simply because the universe is expanding faster than light can travel between us and them. Quietly, we walk into the basic geometry. In a static universe, light could in principle reach any object given enough time. The cosmos would be entirely accessible. Every galaxy would be, eventually, communicable. But in an expanding universe, this is no longer true. As the cosmos expands, distant galaxies recede from us at speeds determined by their distance and the Hubble constant. For galaxies at moderate distances, the recession speed is small compared to the speed of light. For galaxies at greater distances, the recession speed grows. Eventually, the recession's speed exceeds the speed of light. Beyond that distance, light leaving us today will never make up the gap, because the cosmos is stretching faster than the light can cross. The distance at which the recession speed equals the speed of light is called the Hubble radius. The Hubble radius today is about 14.5 billion light-years. Galaxies at that distance are receding from us at exactly the speed of light. Galaxies further away are receding faster than light. This is not a violation of special relativity, because the recession is due to the expansion of space itself, not the motion of the galaxies through space. Pattern interrupt. The Hubble radius is not yet the event horizon. The Hubble radius is the distance at which the recession is currently superluminal. Light leaving us today can, in principle, still reach galaxies somewhat further out than the Hubble radius, because the cosmic expansion rate changes with time, and a photon that starts out behind the Hubble flow can still gain on its target if the expansion decelerates. In a universe with only matter, the expansion would always decelerate, and light could eventually catch up to almost any distant galaxy. But our universe does not contain only matter. It contains dark energy. Dark energy causes the cosmic expansion to accelerate, not decelerate. In an accelerating universe, the Hubble radius is also accelerating outward, but slowly. Meanwhile, distant galaxies are accelerating away from us. The combination produces a true horizon, beyond which light leaving us today will never reach. That distance today is about 16 billion light-years. Walk with me through what this means in practice. Every galaxy currently within about 16 billion light-years of us is, in principle, reachable. We could send a signal toward any of them, and given enough cosmic time, the signal would arrive. Every galaxy currently beyond 16 billion light-years from us is, in principle, unreachable. No signal we send today will ever arrive. The galaxies out there are not invisible in the sense that we can still see them, because their light was emitted in the past, when the cosmos was smaller, and the photons have been propagating toward us ever since. But any signal we send now will never reach them. The relationship between us and the distant cosmos is one way. We can see them. We cannot speak to them. By the end of tonight, you're going to understand that this is one of the most disquieting features of modern cosmology. The event horizon is real, and it is shrinking. Every year, as the cosmic expansion accelerates, more galaxies cross the horizon and become permanently inaccessible. The galaxies are still out there. Their light is still reaching us for now. But the day they crossed the horizon, the future communication channel between us and them was closed. Sit with this. The cosmos is a slow, continuous goodbye. Every moment, somewhere in the sky, a galaxy is crossing the event horizon from our perspective, becoming, in a real sense, unreachable forever. The crossing is not visible. It does not produce a flash or a signature. It is simply a quiet mathematical event, the moment at which our future light cone no longer intersects with the world line of the receding galaxy. After that moment, nothing we can do will ever reach them. Before that moment, communication was in principle possible. After it, not. No one expects, on first hearing about cosmic expansion, that the universe is losing access to its own contents at a measurable rate. No one predicts that the simple geometry of cosmic acceleration would produce a boundary that recedes from us in time as well as in space. Absolutely no one anticipates the way the cosmic event horizon, despite being made of nothing physical, becomes one of the most concrete features of the modern cosmological picture. The second edge, the reachable edge, is therefore not made of any material. It is made of geometry and expansion. It is a property of the relationship between cosmic distances and the cosmic expansion rate. It has no thickness, it has no color, it has no temperature. It is simply the boundary in space-time beyond which our future light cone cannot reach. What we can say about what lies beyond it is limited. We can still see, at the present moment, galaxies that are currently beyond the event horizon because the light from those galaxies left them in the past when the cosmos was smaller and they were within reach of the light. As we observe them, we are seeing them as they were in the past. Their present states are now unreachable to us. We can see what they looked like billions of years ago, but we cannot send a message to them and have it arrive at their present. Picture for a moment how strange this asymmetry is. The reachable edge is a one-way mirror. We can look through it into the past of the distant cosmos. We cannot reach through it into the future of the distant cosmos. The geometry is asymmetric in time. Light leaving them in the past could still reach us today. Light leaving us today cannot reach there tomorrow. Slowly, we trace what happens to galaxies as they approach the event horizon. As a galaxy recedes from us at greater and greater speed, its light becomes more and more redshifted. The galaxy appears dimmer and redder. By the time the galaxy crosses the event horizon, its light is so far redshifted that it has effectively faded into the cosmic microwave background. In the very far future, every galaxy currently visible to us will one by one fade into invisibility as their light becomes too redshifted to detect. The sky will slowly empty of distant galaxies. Only the gravitationally bound members of our local group, the galaxies close enough to remain in our gravitational embrace, will still be visible. Everything else will have faded. The far future of cosmic observation in this picture is a kind of isolation. Civilizations that exist in trillions of years from now will see only the small handful of galaxies that have remained bound to the local group. They will not see, will not know about, will not be able to detect the trillions of galaxies that are currently filling the visible sky. The cosmic web will be invisible to them. The history of the cosmos will be inaccessible to them. They will assume, perhaps reasonably, that the universe consists of one cluster of galaxies surrounded by darkness. What this means is that we are alive during a privileged epoch for cosmic observation. The cosmic web is currently visible. The most distant galaxies are still observable. The CMB is still readable. All of this will, over the next trillion years or so, slowly fade as the cosmic expansion carries everything beyond the event horizon. We are seeing the cosmos at a particular moment in its history, one that future observers cannot. The richness of what we can currently observe is not permanent. Sit with this. Imagine being an astronomer 10 trillion years from now, looking up at a sky that contains only a few hundred galaxies, all gravitationally bound to your local cluster. Without the historical record we are accumulating now, you would have no way to know that the cosmos contained anything more. You would have no CMB to read. You would have no distant galaxies to observe. You would have no evidence of the Big Bang. The universe, as far as your instruments could tell, would consist of a small, isolated cluster of galaxies floating in an apparently infinite void. The truth, the rich, crowded cosmic web that we see today, would be hidden from you behind the event horizon. We are, in this sense, sitting at a moment of unique cosmic visibility. The reachable edge has not yet shrunk so far that the cosmos is fully isolated. It is shrinking. The clock is ticking. Future civilizations, even if they are technologically advanced beyond ours, will inherit a much smaller cosmos than the one we currently inhabit. Take a slow breath here. The story is about to take a brief turn into a different kind of conversation. Before we walk into the third edge, the light edge, We should pause for a moment to acknowledge why this kind of long, slow cosmic story exists at all. Tonight, we're going to walk into the mathematical structure of cosmic horizons because the geometry of an accelerating universe is one of the most beautiful and counterintuitive results in general relativity. The relevant mathematics begins with the work of Willem de Sitter, a Dutch astronomer and mathematician who, in 1917, found one of the first non-trivial solutions to Einstein's field equations. The solution described a universe with no matter, no radiation, and only a cosmological constant. The de Sitter universe expanded exponentially with time, doubling in size at regular intervals forever. The solution was, at the time of its discovery, considered a mathematical curiosity. It did not seem to describe the actual universe, which contained plenty of matter and radiation. A century later, the de Sitter universe has become the asymptotic future of our own. As the cosmic expansion accelerates, driven by the cosmological constant or whatever dark energy actually is, the universe is approaching a de Sitter state. The matter is being diluted by expansion. The radiation is being redshifted into invisibility. What remains in the far future is essentially a de Sitter spacetime, with exponential expansion driven by the cosmological constant. The de Sitter spacetime has a remarkable property. It contains an event horizon for every observer. The horizon is at a fixed distance from the observer, regardless of which direction you look. The horizon has a characteristic radius determined by the cosmological constant. The smaller the cosmological constant, the larger the horizon. The horizon is, in the de Sitter case, eternal. It does not grow or shrink. It simply sits at its fixed distance, marking the boundary of what the observer can ever influence. For our universe, the cosmological constant is not exactly zero, but it is very small. The corresponding de Sitter horizon is large, about 16 billion light-years today. As the cosmos approaches the de Sitter state in the far future, our event horizon will approach this fixed distance and remain there. Galaxies currently beyond the horizon will never come back into view. Galaxies currently within the horizon will, over time, mostly cross outward as the cosmic expansion carries them past the horizon. Only galaxies that are gravitationally bound to us will remain indefinitely within our event horizon. No one expects, when first encountering cosmic acceleration, that the asymptotic future of our universe is a static-looking de Sitter spacetime with a fixed horizon. No one predicts that the rich, crowded cosmos we currently observe will, over the next trillion years, slowly evacuate itself into a near-empty configuration, with only the local group of galaxies as company. Absolutely no one anticipates the way the de Sitter horizon, once an obscure mathematical solution, becomes the defining feature of our cosmic future. Pattern interrupt. The de Sitter horizon has a temperature associated with it. The temperature, calculated by Gary Gibbons and Stephen Hawking in 1977, is determined by the radius of the horizon. The Gibbons-Hawking temperature for our cosmic horizon is extraordinarily small, about 10 to the minus 30 kelvins. This is too small to be detected by any conceivable experiment, but it is not zero. The cosmic event horizon in the de Sitter picture glows faintly in the same way that the event horizon of a black hole glows with Hawking radiation. The cosmic horizon radiates a thermal spectrum with an extremely low temperature in every direction inward toward the observer. The radiation is too faint to matter in any practical sense, but its existence is theoretically important. It means that the cosmic event horizon is not just a geometric boundary, but a thermodynamic object. The horizon has an entropy, calculated from its area, just like a black hole horizon. The entropy of the cosmic horizon is enormous, dominating the total entropy of the observable cosmos by many orders of magnitude. The cosmic horizon in this picture is the largest reservoir of entropy in our future. What this means is that the second edge, the reachable edge, is more than just an event horizon in the geometric sense. It is a thermodynamic surface with temperature, entropy, and radiation. The mathematics treats it, in some respects, as an actual physical object. The horizon has properties. It interacts with the cosmos in subtle ways. It is not simply nothing. Tonight, we're going to acknowledge one more feature of the cosmic event horizon that has become important in recent theoretical work. The holographic principle developed by Gerard Hooft and Leonard Susskind in the 1990s suggests that the information content of a region of space-time is encoded on its boundary, rather than being distributed throughout the volume. For a black hole, the principle implies that all the information about the matter that fell into the black hole is encoded on the surface of the event horizon, not in the interior. For the cosmic event horizon, the principle suggests that all the information about the observable cosmos is encoded on the surface of the horizon, rather than being distributed throughout the cosmic volume. The implications of the holographic principle for cosmology are still being worked out. Some theorists, including Raphael Bousso and his collaborators, have proposed that the cosmic horizon plays a fundamental role in defining the physical content of the observable universe. The principle is at present more theoretical than observational. It has not been directly tested, but it is taken seriously by significant fractions of the theoretical physics community, and it suggests that the second edge, the reachable edge, may be one of the most fundamental features of the cosmos, rather than just a geometric boundary. By the end of tonight, you're going to understand that the cosmic event horizon, once a curiosity of de Sitter spacetime, has become a central object of study in modern theoretical cosmology. The horizon has temperature. The horizon has entropy. The horizon may encode the holographic information content of the observable cosmos. The horizon is, in many ways, the most studied surface in late 20th and early 21st century theoretical physics, alongside the event horizons of black holes themselves. Hold the image. The cosmic event horizon surrounds us in every direction at a distance of about 16 billion light-years. It has a temperature of 10 to the minus 30 kelvins. It has an entropy that dominates the cosmic entropy budget. It may encode the entire information content of the observable cosmos. It is the boundary of our future causal reach, and it is, in the de Sitter limit, the eternal surface that will define the universe for the rest of cosmic history. No one predicts, on first thinking about cosmic geometry, that a horizon could have a temperature. No one expects that the boundary of our future light cone could glow, however faintly, with thermal radiation. Absolutely no one anticipates that the de Sitter horizon, originally derived in a mathematical idealization with no matter at all, would become the asymptotic destination of the actual cosmos we live in. Before we continue, why this channel exists. If you have made it this far into a story about cosmic horizons, you are not the casual viewer the platform expects. You are the person for whom this channel exists. Long-form cosmology told at the pace of sleep, with the time to actually develop a question across multiple chapters and not collapse it into a 5-minute summary, is not what the algorithm rewards. It is what we make anyway, because we believe the cosmos is more interesting at the pace of a slow walk than at the pace of a viral clip. If that resonates with you, the simplest gift you can give is to subscribe. Subscribing tells the platform that long, calm cosmic work is worth surfacing for the next person who needs a quieter way to think about the universe. It also tells us, the people who make these videos, that the audience for this kind of work is real. If you have already subscribed, thank you. Truly. If this is your first long-form cosmic night with the channel, welcome. There are many more nights like this one waiting in the queue. A small additional note. If you find yourself listening on Spotify on a night when you cannot sleep and would rather have a calm voice in the dark, consider following the show there as well. The audio versions are tuned for exactly that purpose, the same length, the same pace. We want to be a slow companion on both surfaces, whichever one finds you when you need it. Now, let us return to the cosmos. The third edge is waiting. The third edge of the universe is the one most people are picturing when they ask the question we are exploring tonight. It is the particle horizon, the light edge, the boundary beyond which we have not yet had enough cosmic time for any photon to cross. The third edge is made of the absence of light. Take a moment to walk into this carefully, because the particle horizon is the most commonly misunderstood of the 5 edges. People assume that the visible universe is 14 billion light-years across, because the universe is 14 billion years old, and light cannot have traveled further than that in the time available. The intuition is reasonable. It is also wrong. The particle horizon today sits at a distance of about 46.5 billion light-years from Earth. This is the radius of the observable universe. The full diameter in any direction is about 93 billion light-years. The reason for the discrepancy is the expansion of the universe. Photons emitted from the surface of last scattering, 380,000 years after the Big Bang, started their journey toward us when the cosmos was much smaller than it is today. As they traveled, the cosmos stretched. The photons arrived at our position 13.8 billion years later, but the points in space from which they were emitted are now much further away than 13.8 billion light-years, because those points have been carried away by the expansion during the photon's journey. The particle horizon is therefore the present distance to the most distant point from which light has had time to reach us since the Big Bang. It is the surface of last scattering, projected to its current cosmic position. The points on the surface of last scattering, where the CMB was emitted, are now about 46.5 billion light-years away from Earth. The light we see from those points was emitted long ago, but the points themselves have been receding from us throughout the journey of the light. No one expects on first encountering the geometry of cosmic expansion that the radius of the observable universe could be 3 times larger than the age of the universe in light-years. No one predicts that the simple intuition of light travel in static space could be so misleading when applied to an expanding cosmos. Absolutely no one anticipates the way the cosmic geometry quietly inflates the apparent size of the observable universe beyond the naive estimate. Pattern interrupt. Sit with the basic picture. The observable universe is a sphere centered on Earth with a radius of about 46.5 billion light-years. Every galaxy, every star, every quasar within that sphere is, in principle, observable. We see them at various times in their past, depending on how long their light took to reach us. The most distant galaxies, currently observed by JWST at the highest redshifts, are seen as they were within a few 100 million years of the Big Bang. The CMB, the most distant thing we can see, is observed from the moment of recombination, 380,000 years after the Big Bang. Beyond the particle horizon, there is no light to be seen. There is no observation possible. The light from those regions has not yet had time to reach us. The third edge, the light edge, is therefore made of darkness in a precise sense. It is the boundary beyond which the cosmos has not yet revealed itself to us in any electromagnetic form. It is the edge of our observation. Walk slowly through what lies beyond the third edge. We have strong theoretical reasons to believe that the cosmos extends, almost certainly, far beyond the particle horizon. The most natural extension of the standard cosmological model is a universe that is, on the largest scales, much larger than the part we can observe, possibly infinite. The standard model treats the cosmic geometry as uniform on average across all scales. There is no reason to expect that the universe simply ends at the edge of our observable horizon. The horizon is a feature of our position and our cosmic age, not a feature of the universe itself. The theoretical estimates for the actual size of the universe beyond the particle horizon vary widely. The most conservative estimates based on extrapolating the observed flatness of the cosmic geometry, suggest that the total universe is at least several hundred times larger than the observable part. More aggressive estimates, based on the dynamics of cosmic inflation, suggest that the total universe may be vastly larger than the observable part, possibly by factors of 10 to 100,000 or more. Some inflationary models produce a multiverse of infinite extent, with regions far beyond our horizon that have entirely different cosmic histories. By the end of tonight, you're going to understand that the third edge, the light edge, is therefore not the edge of the cosmos. It is the edge of what light has had time to bring us. The cosmos almost certainly extends much further. We will never see those distant regions. The particle horizon is a one-way boundary on our knowledge. What lies beyond it is, for now, accessible only through theoretical reasoning, not through observation. This is one of the most disquieting facts in cosmology. The vast majority of the cosmos, by some estimates more than 99.9% of the total, lies beyond our particle horizon. We will never observe it. We can infer its existence only through extrapolation from the part we can see. The unobservable cosmos is, in a strict sense, hypothetical. Its properties are inferred, its behavior is modeled, its observations are not and never will be available to us. What this means for the question of what the edge is made of becomes interesting. The light edge is made of the boundary between the observable cosmos and the unobservable cosmos. It is not a sharp boundary. It is, in a real sense, an arbitrary boundary determined by where we happen to be sitting in cosmic space and time. Move a few billion light-years in any direction, and a different observable cosmos would be defined. Wait a few billion years, and the particle horizon will have grown to include parts of the cosmos currently beyond our reach. The light edge is a personal horizon, defined by our own observational position. For an observer in a distant galaxy, currently beyond our particle horizon, the equivalent horizon would be centered on them, not on us. Their observable universe would include parts of the cosmos we cannot see, and exclude parts of the cosmos we can. The two observable universes would overlap only partially. The boundary between observable and unobservable is observer-dependent. It is, in this sense, a relational property of the cosmos, not an absolute property. For the next stretch, we consider one of the most beautiful features of the light edge. As we look further out toward the particle horizon, we are looking further back in time. The most distant galaxies are seen at their earliest stages. The most distant signal of all, the CMB, is seen at the earliest moment we can directly observe in light. The particle horizon is, in a real sense, both a spatial boundary and a temporal one. It is the spatial location of the most distant photons we can detect, and it is the temporal moment of the earliest light that has been able to reach us. No one expects, on first thinking about the universe's size, that the most distant places in space and the earliest moments in cosmic history would be the same thing. No one predicts that the geometry of cosmic observation collapses spatial distance and temporal distance into a single one-dimensional ladder. Absolutely no one anticipates that the question what is at the edge is also, simultaneously, the question what is at the beginning. The deep implication is that the particle horizon and the surface of last scattering are, from our perspective, essentially the same surface. The CMB is the light from the particle horizon. The particle horizon is the place from which the CMB was emitted. The two concepts coincide because we are looking back to the earliest moment from which any light could have reached us. There is no earlier light to observe, because before recombination, light could not propagate freely. Beyond the surface of last scattering in time lies the era of the opaque plasma. The plasma extends back in time from recombination to the very early universe, all the way to the moment of cosmic origin, whatever that means precisely. We have no direct optical access to that era. The cosmos was, in that period, fundamentally non-luminous to outside observers. The plasma was emitting and absorbing light internally, but no light could escape long enough to be observed today. The Standard Model offers indirect probes of the pre-recombination era. Neutrinos, which decouple from matter much earlier than photons, carry information from a much earlier era and form what is called the cosmic neutrino background. We have not yet detected the cosmic neutrino background directly, but it is predicted to exist with high confidence. Gravitational waves from the very early universe, if they were produced in sufficient abundance by inflation or other early processes, could carry information from even earlier eras. The next generation of gravitational wave detectors, including the proposed LISA mission, may be able to probe these signals. The data suggests that the third edge is not, in the strictest sense, the edge of all possible observation. It is the edge of optical observation. Other types of observation, particularly through neutrinos and gravitational waves, may eventually push back the horizon to earlier moments in cosmic history. The full extent of the cosmic past is, in this sense, still being explored. For now, the third edge, as we can observe it in light, is the surface of last scattering, projected to its present distance of 46.5 billion light-years. The edge is made of the absence of any light we have not yet received. The cosmos beyond it is real, almost certainly very large, and almost entirely inaccessible to our current instruments. Take a slow breath here. The light edge is the most precisely measured of the 5 edges we are walking through tonight. The particle horizon is calculated from the age of the universe, the Hubble constant, and the expansion history, all of which are known to high precision from CMB measurements and supernova observations. The radius of 46.5 billion light-years is not a guess. It is the result of careful calculation using the best cosmological parameters we have. Tonight, we're going to walk into one of the most beautiful results in modern cosmology, the acoustic peaks of the cosmic microwave background. The peaks are the fingerprint of sound waves that propagated through the early universe before recombination, and they tell us in remarkable detail what the cosmos was actually doing during the first 380,000 years. Before recombination, the universe was filled with a plasma of photons, electrons, and protons, all tightly coupled to each other. The coupling meant that any density fluctuation anywhere in the plasma would propagate outward as a pressure wave. The waves were not waves of compressed gas in the ordinary sense. They were waves in the combined photon-baryon fluid, traveling at a speed close to the speed of light divided by the square root of 3. The waves are called baryon acoustic oscillations. When recombination occurred, the photons decoupled from the electrons and protons. The pressure waves were, at that moment, frozen in place. The patterns they had created in the cosmic plasma were preserved in the temperature fluctuations of the CMB. The patterns are visible today as a series of bright peaks in the CMB power spectrum at specific angular scales determined by the geometry of the cosmos and the speed of the pressure waves. Picture for a moment how we measure this. The CMB temperature, when measured across the sky, shows fluctuations of about 1 part in 100,000. The fluctuations are not random. They have a characteristic angular scale which corresponds to the size of the largest sound wave that had time to propagate before recombination. The corresponding angular scale, as seen from Earth, is about 1 degree, roughly twice the angular diameter of the full moon. This is the first acoustic peak. There are additional peaks at smaller angular scales, corresponding to higher harmonics of the same fundamental oscillation. The second peak is at about half a degree. The third peak is at about 1/3 of a degree. The pattern continues out to very small angular scales, where the peaks become weaker and eventually fade into the noise. The full series of peaks forms the CMB power spectrum, which is one of the most measured curves in all of modern physics. No one expects, on first hearing about cosmic structure, that the cosmos before recombination was ringing with sound waves. No one predicts that the temperature variations across the cosmic microwave background today carry the fingerprint of those primordial oscillations. Absolutely no one anticipates the way the acoustic peaks become one of the most precise tools for measuring the cosmological parameters that govern the geometry and contents of the universe. Pattern interrupt. The position and amplitude of the acoustic peaks depend sensitively on the cosmological parameters. The angular scale of the first peak depends on the geometry of the universe. If the cosmos were spatially curved, the angular scale would be different from what it is in a flat universe. The measurement of the first peak position, particularly by WMAP and Planck, has confirmed that the universe is spatially flat to within about 1%. The geometry is consistent with the predictions of inflation, which suggest a flat cosmos as a natural outcome of the inflationary expansion. The relative heights of the first, second, and third peaks depend on the ratio of baryonic matter to dark matter. The peaks are produced by the interplay between gravity, which compresses the plasma, and radiation pressure, which resists compression. The exact balance between gravity and radiation pressure depends on the fraction of the cosmic energy density that is in baryons versus in dark matter. By measuring the heights of the peaks precisely, cosmologists can extract the baryon density and the dark matter density. The Planck measurements give a baryon density of about 5% of the cosmic energy budget and a dark matter density of about 25%. Together, we trace one more remarkable feature of the acoustic peaks. The pattern of sound waves frozen at recombination did not just leave an imprint in the CMB, it also left an imprint in the distribution of matter that subsequently formed galaxies. The dense regions of the plasma at recombination became the dense regions of the matter that collapsed into galaxies. The pattern of acoustic oscillations therefore propagated through cosmic history, becoming visible today in the large-scale distribution of galaxies. The pattern is called the Baryon Acoustic Oscillation Signal, or BAO, in galaxy surveys. The BAO appears as a slight preferred separation between galaxies, at a characteristic distance of about 450 million light-years. The distance corresponds to the size of the sound horizon at recombination, projected forward to the present day by the cosmic expansion. By measuring the BO scale in galaxy surveys at different redshifts, cosmologists can trace the expansion history of the universe across cosmic time. The most ambitious BAO measurements have been made by the Sloan Digital Sky Survey, the BOSS and eBOSS programs, and most recently the Dark Energy Spectroscopic Instrument at Kitt Peak. The DESI Year 1 results, published in 2024, provided BO measurements at multiple redshifts spanning much of cosmic history with extraordinary precision. The combined datasets are now being used to test whether dark energy is a true cosmological constant or whether it varies with time. By the end of tonight, you're going to understand that the acoustic peaks and the BAO signal together provide one of the strongest cross-checks in all of cosmology. The peaks in the CMB tell us what the universe looked like at 380,000 years old. The BO in galaxy surveys tells us how the same pattern evolved over the subsequent 13 billion years. The agreement between the two measurements, after accounting for cosmic expansion, is one of the most precise empirical tests of the standard cosmological model. Hold the image. The cosmos before recombination was a hot, dense plasma threaded with sound waves. The waves had a characteristic wavelength set by the speed of pressure propagation and the age of the universe at the time. The waves were frozen at recombination, leaving their pattern in the CMB temperature variations and in the eventual large-scale distribution of galaxies. We can read the pattern today, more than 13 billion years later, in both the microwave sky and the galaxy survey data. The cosmos still carries the echoes of its early ringing. The textbook does not anticipate that sound waves could survive across the entire age of the universe as a measurable signal. Few of us anticipate that the most precise test of the standard cosmological model would come from comparing two completely different measurements of the same primordial oscillation pattern. Almost nobody anticipates the way the cosmic acoustic peaks, once just a theoretical prediction, would become the precision cosmology workhorse of the past 2 decades. What this leaves us with is a much richer picture of the third edge. The light edge, the particle horizon, is not just a boundary of darkness. It is also a surface on which a precise pattern of sound waves is encoded, and the pattern allows us to extract the entire cosmic parameter set with high accuracy. The visible edge, the CMB, and the light edge, the particle horizon, are essentially the same surface, and they collectively carry the most informative signal in all of cosmology. The cosmos at this distance is the same cosmos we live in. The galaxies at the particle horizon are presumably similar to the galaxies near us, with their own stars, their own planets, their own histories. We see them as they were 13 billion years ago, when the universe was young and they were just beginning to form. The galaxies we see today, at every distance, represent slices of cosmic history layered across the sky. The closest galaxies show us the recent cosmos. The most distant galaxies show us the early cosmos. The CMB shows us the cosmos at 380,000 years old. Together, they form a complete temporal map from the present back to the dawn of light. The fourth edge of the universe is the edge between darkness and structure. It is the era of cosmic dawn, the moment when the first stars and galaxies emerged from the dark ages and the cosmos began to fill with luminous objects. The fourth edge is made of hydrogen and helium, and the first heavy elements forged inside the first stars. It is the chemical edge, the structural edge, the edge between the featureless plasma and the rich cosmic web we now inhabit. Step by step, we walk through the geometry of when this transition happened, because the cosmic dawn is one of the most active frontiers of modern observational cosmology. The James Webb Space Telescope was designed in significant part to study this edge. Its observations over the past 4 years have transformed our understanding of when and how the cosmic dawn began. The basic chronology is this. The Big Bang occurred about 13.8 billion years ago. Recombination, when the cosmos became transparent to light, happened about 380,000 years later. From that moment, the cosmos consisted of a uniform plasma of hydrogen and helium, with traces of lithium distributed nearly perfectly evenly throughout space. There were no stars, there were no galaxies, there were no heavy elements. The cosmos was in this era dim and featureless. The CMB photons that we observe today are the only direct evidence we have of what the cosmos looked like in this era. This featureless period is called the Cosmic Dark Ages. It lasted from recombination until the first stars began to form. The length of the Dark Ages is, in current best estimates, about 100 to 200 million years. During this time, the small density variations in the early plasma, which we observe as the temperature fluctuations of the CMB, slowly grew under the influence of gravity. Dark matter began to collapse into halos, gas began to flow into the deepest gravitational wells. Eventually, somewhere in the cosmos, the first molecular hydrogen clouds cooled and collapsed to the densities required to ignite the first stars. No one expects, on first hearing about cosmic history, that the first stars did not form until 100 million years after the Big Bang. No one predicts that the universe spent a substantial fraction of its early existence in complete darkness, with no luminous objects of any kind. Absolutely no one anticipates the way the Dark Ages, despite being completely invisible, are one of the most theoretically rich epochs of cosmic history. Pattern interrupt. The first stars, when they finally formed, were unlike any star we observe in the modern cosmos. They were made of pure hydrogen and helium, with no heavier elements at all. They had no carbon, no oxygen, no iron. The chemistry of stellar formation, which today is heavily mediated by heavier elements that help cool the gas as it collapses, was much less efficient in the early universe. The first stars, therefore, had to be much more massive than typical modern stars in order to ignite at all. Theoretical models suggest the first stars were typically between 30 and several hundred solar masses, far larger than the typical modern star. These first stars are called population 3 stars. They are the most ancient stellar generation in cosmic history. None of them have ever been directly observed. They lived briefly, perhaps a few million years each, before exhausting their fuel and exploding as the first supernovae. The supernovae scattered the first heavy elements, the products of nuclear fusion inside the first stars, into the surrounding cosmos. These heavy elements became the seeds of subsequent generations of stars, including all the stars we observe today. Together, we trace the cosmic dawn timeline more carefully. The first stars began to form somewhere around 100 million years after the Big Bang. The first galaxies, conglomerations of many such stars, began to assemble shortly thereafter. By around 500 million years after the Big Bang, the cosmos contained a substantial population of small galaxies, each one a knot of stars surrounded by gas. By around 1 billion years after the Big Bang, the cosmos was filling with galaxies at a rapid pace, with much higher star formation rates than the cosmos shows today. The James Webb Space Telescope has been observing this exact era. Since its first science observations in 2022, JWST has detected galaxies at progressively earlier times. The most distant confirmed galaxies are now observed at redshifts above 13, corresponding to cosmic times less than 300 million years after the Big Bang. JADE's GSZ 14-0, discovered in 2024, is the current record holder for the most distant confirmed galaxy, observed at a redshift of about 14.3, corresponding to a cosmic age of about 290 million years. What JWST is finding has been a surprise. The galaxies in the cosmic dawn era are larger and brighter than expected. They contain more stars than the standard models predict for their age. They show signs of significant amounts of heavy elements much earlier than the simple picture would suggest. Some of them appear to have black holes at their centers that are far more massive than expected for their age. The cosmos was, apparently, building structure faster than we thought. By the end of tonight, you're going to understand that this is one of the major active puzzles of modern cosmology. Either the standard model needs revision in the early universe parameters, or our understanding of how galaxies form needs to be updated, or there is something special about the way the cosmic dawn unfolded that the simulations have been missing. The puzzle is real. The data is consistent across multiple JWST programs. The community is working through the implications. Walk slowly through what the cosmic dawn era looked like in terms of what the cosmos was actually made of at the time. The dominant material was hydrogen in both atomic and ionized forms. Helium was the second most abundant element, with about 25% of the cosmic baryon mass. The first heavy elements, primarily carbon, oxygen, and silicon, were being produced inside the first stars and dispersed into the surrounding gas through supernova explosions. The interstellar medium of the cosmic dawn was therefore in a state of rapid chemical enrichment, transitioning from pure hydrogen and helium to a gas that increasingly contained the elements that biology much later would depend on. The cosmic dawn era also included a process called reionization. As the first stars and the first quasars produced ultraviolet light, that light began to ionize the surrounding hydrogen gas in the intergalactic medium. The neutral hydrogen that had filled the cosmos after recombination began to be converted back into ionized plasma. The process happened in patches at first, with bubbles of ionized hydrogen growing around the first luminous sources. Over time, the bubbles merged, and by about 1 billion years after the Big Bang, the entire intergalactic medium was once again ionized. Cosmos became transparent to ultraviolet light at this point, in a different way than it had become transparent to optical and infrared light at recombination. The fourth edge, the cosmic dawn edge, is therefore made of multiple things. It is made of hydrogen in its transition from neutral to ionized. It is made of the first stars, briefly and brightly. It is made of the first heavy elements, scattered into the cosmic gas. It is made of structure emerging from the previously uniform plasma. The fourth edge is the chemical and structural transition between an empty early universe and a richly textured later universe. In what follows, we sit with one specific feature of the cosmic dawn that has become observationally important. The 21 centimeter line of neutral hydrogen. When a hydrogen atom is in its ground state, it can transition between two slightly different energy levels by flipping the spin of its electron relative to its proton. The transition produces a photon with a wavelength of about 21 centimeters in the radio part of the spectrum. The 21 centimeter signal from the early universe, when much of the hydrogen was still neutral, can in principle be observed today as a faint radio signal redshifted from the cosmic dawn era. Several experiments have been built to search for the cosmic dawn 21 centimeter signal. The EDGES experiment, the SARAS experiment, the LEADER experiment, and the planned square-kilometer array are all designed in part to detect this signal. The EDGES collaboration announced a tentative detection in 2018 with an unusual signal that, if confirmed, would suggest the neutral hydrogen was colder than the standard model predicts. The result has not been independently confirmed by other experiments. The status of the 21 centimeter signal from cosmic dawn is therefore, as of the present moment, an active observational puzzle. The textbook does not anticipate that the chemistry of the early universe could be measured through the spin states of single hydrogen atoms across vast cosmic distances. Few of us anticipate that the most active observational tool for studying the cosmic dawn would be a faint radio signal corresponding to a wavelength roughly the size of a forearm. Almost nobody anticipates the way the 21 centimeter line, a quantum mechanical detail of the simplest atom in nature, becomes the key probe of one of the deepest unsolved questions in cosmology. What this leaves us with is a picture of the fourth edge that is being filled in real time, by an extraordinary array of modern instruments. JWST is observing the first galaxies. 21 centimeter experiments are probing the neutral hydrogen between the first galaxies. Theoretical simulations are connecting the two. The cosmic dawn era, which until just a few years ago was almost entirely theoretical, is now being mapped with increasing precision. The fourth edge is becoming visible beat by beat as the instruments improve. Tonight, we're going to spend a longer stretch with the actual JWST measurements of the cosmic dawn era, because the data has been arriving at a pace that has reshaped the field within just a few years. The James Webb Space Telescope was launched on Christmas Day 2021 and reached its operational position at the second Lagrange point in late January 2022. After a 6-month commissioning period, the first science observations began in mid-2022. The telescope was designed to be sensitive in the infrared, with mirrors and instruments optimized for the wavelength range from about half a micrometer to about 28 micrometers. The infrared sensitivity is critical for cosmic dawn observations because the light from the earliest galaxies has been redshifted into the infrared by the cosmic expansion. Visible light from galaxies at redshift 10 or higher appears by the time it reaches us in the infrared. Without infrared sensitivity, we cannot see the earliest galaxies at all. The first deep field observations were released in July 2022. The JWST images showed thousands of galaxies in tiny patches of sky, many of them at higher redshifts than had ever been confirmed by Hubble. Within months, Candidates for galaxies at redshifts above 10 were being identified in JWST data. By the end of 2022, several teams were claiming detections of galaxies at redshifts of 14 or higher, corresponding to cosmic times less than 300 million years after the Big Bang. Pattern interrupt. The early claims were initially viewed with caution by the community. High redshift galaxy candidates are notoriously difficult to confirm. Without spectroscopic verification, the candidates can sometimes turn out to be lower redshift galaxies whose colors mimic the high redshift signature. The community waited for spectroscopic follow-up before accepting the initial photometric claims. The spectroscopic follow-up came in 2023. The JWST NISPEC instrument was used to obtain spectra of the most promising candidates. The spectra confirmed that several of the candidate galaxies were genuinely at very high redshifts. The galaxy designated JWST Z13 was confirmed at a redshift of about 13.2. The galaxy JWST Z14, announced in 2024, was confirmed at a redshift of about 14.3. These spectroscopic confirmations established that was, in fact, seeing genuine galaxies from the cosmic dawn era. Walk with me through what these galaxies look like. JWST Z14 is observed as it was about 290 million years after the Big Bang. It contains, by current estimates, a stellar mass of about 400 million solar masses. It is luminous in the rest frame ultraviolet, indicating that it is actively forming stars. Its angular size is small, corresponding to a physical diameter of perhaps a few hundred light-years. It is a small, young galaxy, but it is more luminous than the standard models predicted for galaxies of this age. The discovery of JWST Z14 and similar galaxies has generated an active debate in the cosmology community. The galaxies appear too bright and too massive for their age. The standard models of structure formation predict that galaxies at redshift 14 should be smaller, fainter, and less developed than the JWST observations show. The discrepancy is not enormous, but it is significant. Multiple research groups have published analyses suggesting that the standard model needs revision, or that the early universe was forming structure more efficiently than the standard simulations indicate. The proposed explanations for the discrepancy fall into several categories. Some researchers have suggested that the initial mass function of stars was different in the early universe, with a higher fraction of massive luminous stars compared to today. This would make early galaxies brighter for the same stellar mass. Others have suggested that the first generations of stars were more efficient at converting gas into stars, perhaps because the absence of heavy elements made the gas cooling and collapse process work differently. Still others have suggested that dark matter halos in the early universe were more abundant or more concentrated than the standard simulations predict. By the end of tonight, you're going to understand that none of these explanations has yet been confirmed. The data is consistent with several possibilities. Distinguishing between them will require additional observations, including spectroscopy of more high redshift galaxies, deeper imaging to detect the faintest objects, and theoretical work to refine the predictions of the various models. The cosmic dawn era is, in this sense, one of the most active observational frontiers in modern cosmology. JWST has also detected indirect evidence for early supermassive black holes. The galaxy GNZ11, originally discovered by Hubble at a redshift of about 10.6, has been reobserved by JWST with detailed spectroscopy. The spectra reveal evidence of an active galactic nucleus powered by a supermassive black hole of perhaps several million solar masses. The black hole is, in cosmic terms, a giant for its age. The standard models of black hole formation struggle to explain how a black hole of this mass could have formed within the first 400 million years of cosmic history. Several proposed mechanisms for forming such massive early black holes have been investigated. Direct collapse black hole formation, in which a massive primordial gas cloud collapses directly into a black hole without going through a stellar phase, can in principle produce seeds of tens of thousands of solar masses. These seeds could then accrete rapidly to reach the observed black hole masses. Alternatively, primordial black holes, formed in the very early universe from quantum density fluctuations, could provide an even earlier seed population. The mechanisms are not exclusive. Multiple processes may contribute to the population of early supermassive black holes. No one expects, on first thinking about cosmic structure formation, that the most pressing puzzle in early universe cosmology would be how to make galaxies and black holes too big too fast. No one predicts that JWST's most important contribution would be to put pressure on the standard models of structure formation by detecting more extreme objects in the cosmic dawn era than the models accommodated. Absolutely no one anticipates the way the most expensive telescope ever built would, within its first 2 years of operation, generate a wave of theoretical revision in early universe cosmology. Pattern break. The JADE survey, the Cosmos Web survey, the SEERS survey, and other JWST programs are continuing to collect data. The picture is being filled in week by week. By the end of the JWST primary mission, expected to extend for at least another decade, the cosmic dawn era will be one of the most densely observed regions of cosmic history. The current puzzles will be either resolved or sharpened. The standard model of structure formation will either be confirmed in modified form or replaced by something better. Tonight we're going to acknowledge that the fourth edge, the cosmic dawn edge, has gone from being a theoretical prediction to being an observational frontier in the span of just a few years. JWST has made the cosmic dawn directly observable. The first stars themselves remain just beyond the current detection limit, but the first galaxies, which contain the first stars and the products of the first supernovae, are now being mapped systematically. The chemical edge of the cosmos, the transition between the dark plasma and the structured universe, is being filled in by direct measurement. Mark this moment. The fourth edge is the only one of the 5 edges that is in a sense transitional. The other edges are fixed features of the cosmic geometry. The visible edge will always be the CMB. The reachable edge will always be the cosmic event horizon. The light edge will always be the particle horizon. The theoretical edge will always be the boundary between known physics and speculation. The cosmic dawn edge, by contrast, was a process. It happened over a few 100 million years. It transformed the cosmos from a dark uniform plasma into a richly textured network of galaxies. The fourth edge is the only one with a beginning and an end in cosmic time. By the time the cosmic dawn was complete, the cosmos looked recognizable. The structure we see today, the galaxies and the clusters and the filaments and the voids, was already in place in primitive form. The chemistry was richer. The complexity was emerging. From the end of the cosmic dawn, the path to the present moment is a long, slow continuation of the trends that began during it. More stars, more galaxies, more heavy elements, more planets. Eventually, on at least one of those planets, the chemistry of stars led to the chemistry of biology, and the cosmos became, in our own small corner of it, aware of itself. The fourth edge is, in this sense, the edge between cosmic infancy and cosmic maturity. It is the moment when the universe stopped being a uniform plasma and started being a textured cosmos. Everything that has happened since, every star we have seen, every planet we have detected, every biosphere we suspect exists out there in the dark, is a continuation of the structures that emerged during cosmic dawn. The fifth edge of the universe is the strangest one of all, because the fifth edge is the boundary between what we can describe with modern physics and what lies beyond our current theories. The fifth edge is not located at any specific distance. It is located at the limits of our understanding. Tonight, we're going to walk into this carefully, because the fifth edge is where cosmology becomes speculation, and the line between the two is more interesting than either one alone. The standard cosmological model, the LCDM model that has been our best theoretical framework for the past 3 decades, describes the cosmos from a small fraction of a second after the Big Bang up to the present moment, with extraordinary precision. The model accounts for the expansion history of the cosmos, the cosmic microwave background, the structure of galaxy clusters, the distribution of dark matter, and the accelerating expansion driven by dark energy. The model is, by every reasonable metric, one of the most successful theoretical frameworks in the history of physics, but the model has limits. It does not describe the moment of cosmic origin itself. It does not describe what happened before the very early high-temperature, high-density phase that produced the cosmos we observe. It does not describe what lies beyond the observable horizon. It does not, in its standard form, describe whether the cosmos is finite or infinite. The standard model is silent on these questions because the questions extend beyond the regime where the model has been tested. Beyond the limits of the standard model, theoretical cosmologists have proposed extensions. Some of these extensions are well developed. Others are speculative. None of them have been directly tested. The fifth edge, in this sense, is made of theoretical proposals that may or may not turn out to describe reality. It is the edge of physics itself, the boundary between what we have confirmed and what we have only imagined. Hold the picture as we walk through the leading candidate for what lies just beyond the standard model. The leading candidate is cosmic inflation. Inflation, first proposed by Alan Guth in 1980 and developed by André Linde, Paul Steinhardt, Andreas Albrecht, and others through the 1980s and 90s, is the theory that the cosmos underwent an extraordinarily rapid period of exponential expansion in its very earliest moments. The expansion stretched the universe by a factor of at least 10 to the 26th power in a tiny fraction of a second, taking what was originally a microscopic region of hot, dense plasma and inflating it to the size of a basketball, or possibly much larger. Inflation solves several problems that the standard Big Bang model could not explain on its own. It explains why the cosmos is so spatially flat. It explains why the cosmic microwave background is so uniform across regions that, in the standard model, could not have been in causal contact with each other. It explains the origin of the tiny density fluctuations that seeded the formation of structure. It explains the absence of magnetic monopoles, exotic particles that some grand unified theories predict should have been produced in abundance in the early universe. The successes of inflation are substantial, and the framework is now part of the standard cosmological narrative. Pattern interrupt. The interesting question for tonight is what happens at the end of inflation. In most versions of the theory, the field that drives inflation, called the inflaton, decays into normal particles when inflation ends. The decay process produces the hot, dense plasma that we observe today as the early universe. But in some versions of the theory, particularly those associated with André Linde's eternal inflation framework, the decay does not happen everywhere at the same time. Some regions of the inflating cosmos stop inflating earlier than others. Those regions become individual universes with their own observable histories. The rest of the cosmos continues to inflate. New regions continually pinch off and become new universes. The result is a multiverse, in which our observable universe is one of an infinite number of bubble universes, each with its own properties and possibly its own laws of physics. The multiverse is, depending on which inflationary model you take seriously, a robust prediction of inflation or a speculative extension. The community is divided on how seriously to take it. The leading proponents argue that eternal inflation is the most natural outcome of well-motivated inflationary models, and that the multiverse is therefore a generic prediction of the framework. The leading skeptics argue that eternal inflation depends on specific assumptions that may not be justified, and that other models can produce the cosmic features we observe without requiring a multiverse. Both camps include serious researchers. The debate is active. No one expects, on first encountering inflation, that the simplest extension of the standard cosmological model could naturally lead to an infinite number of parallel universes. No one predicts that the theoretical framework most successful at explaining the observed cosmic features would also imply the existence of regions of reality forever beyond our access. Absolutely no one anticipates the way the fifth edge, once you take inflation seriously, dissolves into something much stranger than a simple boundary. Together, we trace what the multiverse would look like if it is real. In the eternal inflation picture, the inflating cosmos is a vast, possibly infinite, expanding region. Within this region, individual bubble universes nucleate, like bubbles of less dense vapor forming inside a pot of water that is approaching the boiling point. Each bubble is a universe in its own right. The bubble we live in has had 13.8 billion years of internal cosmic history. Other bubbles are at different stages. Some are younger, some are older. The inflating cosmos surrounding the bubbles continues to expand, producing more bubbles over time. There is no center, no edge, no end to the process. The multiverse in this picture has been producing universes forever and will continue doing so forever. The properties of the bubble universes need not be the same as ours. The constants of nature, including the strength of gravity, the masses of fundamental particles, and the value of the cosmological constant, may take different values in different bubbles. Some bubbles may have no stars, because the constants do not permit nuclear fusion. Some bubbles may have no atoms, because the electromagnetic interaction is too weak or too strong. Some bubbles may have entirely different sets of fundamental forces. The cosmic landscape in this picture is vast. Our bubble is one of perhaps an unimaginable number, each with its own internal physics. By the end of tonight, you're going to understand that this is the most speculative part of the night. The multiverse, in the eternal inflation framework, is not directly observable. Bubbles other than our own are causally disconnected from us. Their existence cannot be confirmed by direct observation, even in principle. We can argue for them only through theoretical reasoning, by extrapolating the assumptions of our cosmic models. The multiverse is, in this sense, a hypothesis that may always remain a hypothesis. The fifth edge is, in this version, made of theoretical inference, not material observation. Take a slow breath here. The fifth edge has alternatives within mainstream cosmology. Some theorists, particularly Roger Penrose, have argued for conformal cyclic cosmology, in which the cosmos goes through endless cycles of expansion and collapse, with each cycle producing a new universe out of the cold dilute remnants of the previous one. In this picture, what lies beyond our cosmic past is the previous cycle, the cosmos before our Big Bang. Other theorists, drawing on string theory, have proposed cosmologies in which the cosmos is described by mathematics in 11 or more dimensions, with the four-dimensional space-time we observe being a slice through a higher dimensional structure. Still others have proposed loop quantum cosmology models, in which the Big Bang was not a beginning but a bounce, with a previous contracting cosmos producing the expanding one we observe. Each of these alternatives produces a different answer to the question of what lies at the fifth edge. In the eternal inflation picture, the fifth edge is a multiverse of bubble universes. In the cyclic picture, the fifth edge is the previous cosmic cycle. In the higher dimensional picture, the fifth edge is the additional dimensions of the cosmic geometry. In the loop quantum picture, the fifth edge is the contracting cosmos that preceded our Big Bang. Quietly, we hold all four answers as live possibilities. Each one is a serious theoretical proposal. Each one has been developed by competent researchers. Each one has been published in major journals. None of them has been directly tested. The fifth edge in current physics is the boundary at which our experimental access ends and our theoretical reasoning takes over. The reasoning is not random. It is constrained by mathematics, by the requirement of consistency with what we already observe, by aesthetic considerations of simplicity and elegance. But it is not the same kind of knowledge as the knowledge we have about the first four edges. The fifth edge is in this sense more open than the others. Hold the thought. The fifth edge is also the only edge for which we may eventually obtain experimental access. The other edges are fixed by the cosmic geometry and will remain at their current positions as the cosmos evolves. The fifth edge could, in principle, be pushed back as our theories improve. Future experiments may detect signatures of the very early universe that constrain inflationary models more tightly. Future observations may detect gravitational waves from cosmic inflation itself, which would provide direct evidence about the dynamics of the inflationary era. Future theoretical work may identify ways to test the multiverse hypothesis, perhaps through subtle imprints of bubble collisions on the CMB or through more indirect methods. The future of the fifth edge is, in this sense, open in a way the other edges are not. We may, over the coming decades and centuries, push it back. We may, on the other hand, find that it stays where it is, an absolute boundary on what physics can describe. The answer is not yet known. Tonight, we're going to walk through the actual history of inflation as a theory, because the development of the framework is one of the great stories of late 20th century theoretical physics, and the open questions about it sit at the heart of the fifth edge. The story begins in 1979 with Alan Guth, then a young postdoctoral researcher at the Stanford Linear Accelerator Center. Guth had been working on grand unified theories, the proposed extensions of the standard model of particle physics that would unify the electromagnetic, weak, and strong forces into a single framework at very high energies. Grand unified theories predicted that in the early universe, magnetic monopoles should have been produced in abundance, but no magnetic monopoles had ever been observed. The discrepancy between the theoretical prediction and the observational absence was called the monopole problem. Guth was trying to find a mechanism that would dilute the predicted monopole population to undetectable levels. He worked through a scenario in which the early universe underwent a brief period of exponential expansion driven by the energy of a metastable false vacuum. The exponential expansion would stretch the cosmic geometry so dramatically that any monopoles produced before the expansion would be diluted to densities far below any observable threshold. The same expansion would also explain why the cosmic microwave background is so uniform across regions that, in the standard Big Bang picture, could not have been in causal contact with each other. The mechanism solved the monopole problem and the horizon problem simultaneously. Guth published the proposal in 1981 in a paper that has become one of the most cited papers in modern cosmology. The framework was called inflation. It quickly attracted the attention of theoretical cosmologists who recognized that it could solve a substantial number of outstanding puzzles in the standard Big Bang model. The initial version of inflation, however, had a problem. The exponential expansion was supposed to end through a process called bubble nucleation, in which the false vacuum decayed into the true vacuum in random patches throughout the inflating cosmos. The patches would expand at the speed of light, eventually merging to fill the cosmos with the true vacuum and end the inflationary expansion. But Guth's original mechanism produced inflation that lasted too long, so that the patches were diluted by the ongoing expansion and could not merge effectively. The cosmos would end up as an inhomogeneous mess of bubble interiors and inflating regions, not the smooth uniform cosmos we observe. The fix came from Andrei Linde, an exiled Soviet physicist who would later move to Stanford, and independently from Andreas Albrecht and Paul Steinhardt at Penn State. They proposed a modified version of inflation, sometimes called new inflation or slow roll inflation, in which the inflaton field rolls slowly down a gentle potential rather than tunneling through a barrier. The slow roll mechanism produces a graceful end to inflation, with the cosmos transitioning smoothly into the standard hot Big Bang phase. The graceful exit problem was solved. By the mid-1980s, slow roll inflation had become the standard inflationary framework. Lindy subsequently proposed several extensions and refinements, including the eternal inflation framework that has become the basis for modern multiverse cosmology. The framework has continued to develop, with hundreds of specific inflationary models proposed and analyzed over the decades since. No one expects, in the original development of inflation, that the theory would become a vast landscape of competing models rather than a single specific framework. No one predicts that the inflationary potential, the function that describes how the inflaton field behaves, would turn out to be largely unconstrained by the data. Absolutely no one anticipates the way inflation, while solving the original problems Guth was working on, would generate its own set of theoretical and observational questions that remain open 4 decades later. Pattern interrupt. The key prediction of inflation that has not yet been confirmed is the existence of primordial gravitational waves. Inflation predicts that quantum fluctuations of the spacetime geometry during the inflationary expansion should have produced gravitational waves with a specific spectrum propagating across the cosmos ever since. The gravitational waves would imprint a characteristic pattern on the polarization of the CMB called the B-mode signal. Detection of the B-mode signal would provide direct evidence for inflation. Non-detection would constrain the inflationary parameter space. Multiple experiments have searched for the B-mode signal. The BICEP collaboration, operating at the South Pole, made a tentative detection in 2014, but the signal turned out to be largely produced by galactic dust rather than primordial gravitational waves. The Planck satellite, the Keck array, and the Spider experiment have all placed upper limits on the B-mode signal that are now constraining the most aggressive inflationary models. The next generation of experiments, including the Simons Observatory, CMBS-4, and the Lightbird satellite, are designed to detect the B-mode signal at a level that would distinguish between major classes of inflationary models. By the end of tonight, you're going to understand that the search for primordial gravitational waves from inflation is one of the major experimental programs of the next 2 decades. If the signal is detected, the discovery would represent direct observational evidence for the inflationary expansion itself, pushing the boundary of cosmology back to within 10 to the minus 35 seconds of the Big Bang. If the signal is not detected at the sensitivity these experiments will reach, the constraint on inflationary models will be severe, and significant fractions of the inflationary landscape will be ruled out. Together, we acknowledge that the fifth edge is not just speculative philosophy, it is also an experimental frontier. The boundaries between known and unknown physics are being pushed back by carefully designed experiments. The future of the fifth edge depends, in part, on what these experiments find. The B-mode searches are perhaps the most important single program, but they are not the only one. Gravitational wave detectors like LISA, planned for launch in the 2030s, may also probe the very early universe through other channels. The neutrino observatories, including IceCube and the planned Hyper Kamiokande, may eventually detect the cosmic neutrino background, providing another window into the pre-recombination cosmos. Hold the image. The fifth edge, the theoretical edge, is the boundary between the standard cosmological model and the proposed extensions. The extensions include inflation, the multiverse, cyclic cosmology, and higher dimensional theories. Some of the extensions, particularly inflation, have made specific testable predictions that experimental programs are currently pursuing. Other extensions, particularly the multiverse, may always remain beyond direct observational test. The fifth edge is, in this sense, partly experimental and partly philosophical. The experimental part is moving forward. The philosophical part is being argued out in journals and conferences. The textbook does not anticipate that the boundary of cosmological knowledge could be pushed back by polarization measurements of the cosmic microwave background. Few of us anticipate that the most distant feature of physical reality, the moment of cosmic inflation, would be probed through tiny patterns in the polarization of microwave radiation arriving from every direction. Almost nobody anticipates the way the fifth edge, despite being the most theoretical of the five edges, has become one of the most experimentally active frontiers in modern physics. What this leaves us with is a fifth edge that is partly known and partly unknown, with the boundary between the two being slowly pushed back by the work of multiple experimental and theoretical communities. Inflation may or may not be the correct description of the very early universe. The multiverse may or may not be a real feature of the cosmos. The cyclic models may or may not describe the cosmic past and future. The theoretical edge is, in this sense, the most alive of the five edges. It is changing in real time as the experiments and theories evolve. Slow turn. What this leaves us with is a complete picture of the five edges, each one with its own physics, its own materials, and its own answer to the question we asked at the start of the night. The first edge, the visible edge, is made of light. It is the CMB, the surface of last scattering, the cooled remnant of the hot plasma that filled the early universe. We can measure it precisely. We can read its temperature variations and extract the parameters of cosmic geometry. The visible edge is the most directly observed of the five. The second edge, the reachable edge, is made of expansion. It is the cosmic event horizon, the distance beyond which the accelerating cosmos has carried galaxies forever beyond our communicative reach. The reachable edge has no thickness, no color, no temperature. It is a geometric property of an accelerating cosmos. The third edge, the light edge, is made of darkness. It is the particle horizon, the distance beyond which light has not yet had time to reach us since the Big Bang. The light edge is the boundary of our observable cosmos. Beyond it, the universe almost certainly continues, but the photons have not yet arrived. The fourth edge, the cosmic dawn edge, is made of the first stars and the first galaxies emerging from the dark ages and lighting the previously featureless cosmos. The fourth edge was a process, not a place. It happened over a few 100 million years, and it transformed the cosmos from a uniform plasma into a structured network of galaxies. The fifth edge, the theoretical edge, is made of inference, of mathematics, of speculation. It is the boundary between the standard cosmological model and the extensions, including inflation, the multiverse, cyclic cosmology, and higher dimensional theories. The fifth edge is the open frontier of cosmology, the place where the questions are sharper than the answers. Five edges, five materials, five answers to a question that turns out to have been simpler in its asking than in its answering. Tonight, we're going to step back from the five edges and ask a question that ties all of them together. Why is this particular moment in cosmic history such a strange and privileged moment for asking the question we have been asking? Before we get started on the answer, sit with the basic shape of the situation. We are alive in a universe that is 13.8 billion years old. The universe will, in all likelihood, continue to exist for at least another 100 billion years before the slow heat death begins to dominate. We are sitting, in other words, at less than 14% of the way through cosmic history in any conventional measure. By cosmic standards, we are still in the early afternoon. But the picture changes dramatically when we ask how much of cosmic history we can directly observe from here. We can observe back to the moment of recombination, 380,000 years after the Big Bang. We cannot observe any earlier in light. We can observe forward only the present moment, we cannot observe any future at all. The window of cosmic time available to us in direct observation is the 13.8 billion years of cosmic past and 0 years of cosmic future. Now, let's begin to think about how that window changes with cosmic time. The visible edge of the cosmos, the CMB, is currently observed at a temperature of about 2.7 kelvins. As the cosmos continues to expand, the CMB will continue to cool. Over the next billion years, the CMB temperature will drop by a small fraction. Over the next 100 billion years, the CMB will be cooler by perhaps a factor of 3 or 4. By the time the cosmos reaches an age of about 1 trillion years, the CMB will be cooler than the cosmic background of the local group itself, and it will no longer be distinguishable from the thermal noise of the surroundings. Expectation. The CMB is a permanent feature of the cosmos, available to any future civilization that develops the technology to detect it. Reality. The CMB is fading. The signal is not eternal. There is a finite window of cosmic time during which the CMB is detectable. We are alive inside that window. Future civilizations will not have it. Soft pause. The reachable edge has the same kind of finite window property, but in reverse. The cosmic event horizon today sits at about 16 billion light years. As the cosmos accelerates, galaxies that are currently within the horizon are being carried, one by one, past it. By the time the cosmos is 1 trillion years old, almost all of the galaxies currently visible will have crossed the event horizon. The visible cosmos will have shrunk to the gravitationally bound local group. The cosmic web will be invisible. The structure of the cosmos beyond our cluster will be unobservable. Now, let's begin to count what this loss means. Today, with our instruments, we can see roughly 200 billion galaxies. In the far cosmic future, the number of visible galaxies will be perhaps 50, all members of our local cluster. The information content of the future cosmic sky is dramatically smaller than the information content of the present cosmic sky. We are not just losing access to distant galaxies, we are losing access to the cosmic web itself. What follows from this is that this implies something profound about our position in cosmic history. We are alive during one of the only epochs in the entire cosmic future in which the full cosmic web is visible. Before recombination, there was no light at all. Between recombination and the first galaxies, the cosmos was dark and featureless. From the cosmic dawn through the present moment, the cosmic web has been progressively illuminated by the formation of stars and galaxies. From now into the deep future, the cosmic web will progressively fade as galaxies cross the event horizon and disappear from observation. Expectation. Cosmic observation will continue to improve indefinitely as instruments become more sensitive. Reality. Cosmic observation has a peak window, and we are alive inside it. Civilizations in the deep future will inherit a much emptier cosmos than the one we currently observe, no matter how good their instruments become. Before we get started on what this implies philosophically, take a slow breath here. The window is not infinitely narrow, it is on the order of tens of billions of years. We are not exactly at the center of it. We are perhaps somewhat past the middle, with the future fading more rapidly than the past has cleared up. But the window is finite. The privileged epoch is real. We are not in a generic moment of cosmic history. We are in a particular one. Few would anticipate, on first thinking about cosmic time, that the window of maximum cosmic visibility would turn out to be a measurable feature of cosmology. Few of us anticipate that the question of when in cosmic history to be alive would have a serious cosmological answer, and that the answer would place us more or less right where we are. Almost nobody anticipates the way the fine-tuning of our cosmic timing for observational access becomes part of the modern picture of where we sit in the universe. Let the picture settle. The window has a name in some recent theoretical work. It is sometimes called the cosmic information era, or the rich observation epoch. The basic idea is that the cosmos has only a finite period of time during which it is dense enough to be richly populated with luminous structure, but not yet so dispersed by accelerating expansion that the structure has become invisible. Outside this window, in either direction, cosmic observation is dramatically poorer. We happen to be alive inside the window. Now, let's begin to think about how the five edges relate to this windowed picture. The visible edge, the CMB, is present throughout the rich observation epoch, but will fade after it. The reachable edge, the event horizon, defines the loss process by which the window will eventually close. The light edge, the particle horizon, grows slowly with time, but the growth is more than offset by the loss of access to distant galaxies. The cosmic dawn edge happened once, in the past, and is fading from observation as the cosmos ages. The theoretical edge is, in this picture, the only edge that may genuinely improve with cosmic time as future physics is developed and the boundary of theoretical knowledge moves back. The standard story, the cosmos, is a steady, ongoing structure that we are gradually mapping with better instruments. The reality, the cosmos is a transient structure that we are mapping during a particular window of visibility, after which much of what we currently see will become inaccessible. Hold this fact for a moment. This changes the emotional tone of cosmic observation in a subtle way. The richness of the present cosmic sky is not a permanent feature. It is a temporary configuration, available during a particular epoch. We are not merely observers of an eternal cosmos. We are observers of a cosmos that is in some ways briefly showing us as much as it ever will. The view will not improve forever. The view will, after a long stretch of cosmic time, begin to fade. We are looking at it during one of its peak moments. Before we get started on the close, sit with one more reflection. The five edges we have walked through tonight are not just abstract geometric features. They are the structure of cosmic observation itself, the framework within which any observer in any era must operate. Civilizations across the cosmos, in any galaxy where they may exist, are subject to the same five edges. The visible edge of the CMB is the same for them as for us. The reachable edge of the event horizon is the same. The light edge of the particle horizon is the same, though centered on their position rather than ours. The cosmic dawn edge is the same. The theoretical edge depends on their physics, which may or may not match ours. The five edges are in this sense universal. They are not features of the cosmos that depend on the observer's position in space. They are features of the cosmos that depend on the observer's position in time. Any civilization that exists at 13.8 billion years after the Big Bang, anywhere in the cosmos, would see roughly the same five edges that we see. Civilizations at very different cosmic times would see different versions of the edges. Few of us anticipate that the structure of cosmic observation has a universal character that depends on cosmic time but not on cosmic position. Few would anticipate that the question of what is at the edge of the universe has in this sense a partly time-dependent answer. Nothing in the standard story predicts that observers in the early or late universe would inherit fundamentally different observational situations from observers like us. But that is what the careful cosmological analysis reveals: expectation. The cosmic situation we inherit is the same as the cosmic situation any other observer would inherit. Reality. Our cosmic situation is specific to our cosmic time. Earlier or later observers would have different access to different aspects of the cosmos. A slow turn. Hold this thought. We are, in a real and measurable sense, alive in the right era for the question we have been asking tonight. If we had been alive 10 billion years earlier, the cosmic dawn would still be in progress and the CMB would be hotter, but the cosmic web would not yet have formed. If we had been alive 10 trillion years later, the cosmic web would have faded and only the local group would remain visible. We are alive during the period when the cosmos is at its most observationally rich. The five edges, as they currently stand, are the most complete cosmic picture that any observer in cosmic history is ever likely to have access to. What this leaves us with is a quiet sense of timing. The cosmos has in its own slow way given us a window. The window will not last forever. The view from inside the window is the best view there has ever been or ever will be. Tonight, we have walked along the boundary of that view in 5 different directions. We have visited each edge. We have seen what each one is made of. We have, in some sense, taken inventory of what the cosmos is currently willing to show us. What emerges from this is that this is part of why the question of the edge of the universe is worth asking at all. The edges are not just curiosities, they are the structure of what we are allowed to know. They are the framework within which all future cosmological discovery will operate. They are the limits of cosmic knowledge for any civilization at any cosmic time, with the specific limits depending on when in cosmic history the civilization exists. We are tonight sitting in the right window. The cosmos is at its most luminous. The instruments are improving. The questions are getting sharper. The answers in some cases are emerging. The 5 edges are being mapped, beat, by the work of thousands of scientists across decades. The map is not complete. The map is the most complete it has ever been. The map is being added to every year. Before we walk into the final close, take a moment to acknowledge this. You are alive at a privileged cosmic moment. The cosmos has, in some sense, given you a view it has never given anyone before and will not give anyone again. The view is the night sky outside, layered on top of all the cosmic structure we have mapped through telescopes and theoretical work. The view is the 5 edges, sitting in their places around you. The view is, in its quiet and patient way, the best view there has ever been of the universe we live in. Tonight, we are going to spend some careful time with the 5 most common misconceptions about the edge of the universe, because each one is worth addressing directly, and each one sits at a specific point in the geometry we have already walked through. Now, let's begin with the first misconception. The misconception is that the universe has a physical edge, like the edge of a table or the boundary of a swimming pool. This misconception is so common that almost every popular astronomy question on the subject begins with some version of it. People ask what is beyond the edge of the universe, as if there must be something outside. Before we get started on the correction, sit with why the misconception is so persistent. Everything in our daily experience has edges. Rooms have walls, continents have shorelines, planets have surfaces, stars have boundaries beyond which the density drops to interstellar levels. The intuition that everything must have an edge is strong, because we have never, in any human experience, encountered something that genuinely extends without limit. The cosmos is the first such object most of us are asked to imagine. The correction is that the universe, as far as our measurements can determine, does not have a physical edge. It does not end somewhere. There is no wall, no boundary, no shoreline. The cosmos extends in every direction, at least as far as we can measure, and probably much further than that. What we call edges, the 5 edges we have walked through tonight, are not boundaries of the cosmos itself, but boundaries of our access to it. The cosmos is, in the strongest sense modern cosmology can defend, much larger than the part we can observe. There is no outside. No one expects, on first being told this, that the cosmos could genuinely extend without limit in every direction. No one predicts that the question what is beyond the edge has no observational answer, because the question presumes a structure the cosmos may not actually have. The textbook does not anticipate the way the most natural question about the universe turns out to be the wrong question in a precise scientific sense. Now let's begin with the second misconception. The second misconception is that the Big Bang was an explosion in space, with the cosmos expanding outward into a pre-existing void. The image is vivid, a point of dense matter exploding outward, with stars and galaxies flying away from a central point. Before we get started on the correction, Take a moment to acknowledge that this misconception has been reinforced by decades of popular illustrations and science fiction. The image of the Big Bang as an explosion is everywhere. It is wrong. The correction is that the Big Bang was not an explosion in space. It was an expansion of space itself. There was no center. There was no pre-existing void into which the cosmos expanded. The cosmos has, from the earliest moments we can describe, been filling all of space. The expansion is the stretching of the cosmic geometry, not the motion of matter through a static background. Every point in the cosmos is moving away from every other point. There is no central point from which everything is moving. The cosmos does not have a center, in the same sense that the surface of an inflating balloon does not have a center on its surface. What emerges from this is that this distinction matters profoundly. The Big Bang did not happen at a particular location in space. It happened everywhere simultaneously. The cosmic microwave background is not the residue of an explosion at one place. It is the residue of the hot, dense early phase, distributed throughout all of space. The visible edge of the cosmos, the CMB, surrounds us not because the explosion happened in front of us, but because we are looking back in time in every direction, and every direction eventually reaches the moment of recombination. Now let's begin with the third misconception. The third misconception is that the universe is expanding into something. This is closely related to the second misconception, but distinct from it. People imagine the cosmos as a ball that is growing inside a larger empty space. The correction is that the universe is not expanding into anything. The expansion is internal. There is no exterior. The cosmic geometry is stretching, but the stretching does not require an outside. The mathematical description of the expansion in general relativity treats the universe as a self-contained space-time that grows with time without requiring any external space for the growth to happen in. The cosmos is, in this sense, all there is. The cosmos is not embedded in a higher space. The cosmos is the highest space. No one predicts, on first thinking about expansion, that something could grow without growing into anything. The intuition fights this idea hard, but the mathematics is clear. The expansion is a property of the internal geometry of the cosmos, not a motion of the cosmos through an external space. There is no exterior. There is just the cosmos, which is getting larger over time. Now, let's begin with the fourth misconception. The fourth misconception is that if we could just travel far enough or fast enough, we could reach the edge of the universe. This misconception assumes that the edge is a place that exists in space, and that with enough propulsion technology, we could in principle visit it. The correction is that the edges we have walked through tonight are not places in space. The visible edge, the CMB, is a moment in cosmic history, projected to its current cosmic position. It is, in some sense, a place, but it is also a time. We cannot travel to it. By the time we arrived at its current spatial position, billions of years would have passed, and the matter that emitted the CMB would have evolved into galaxies, stars, planets, and possibly civilizations, none of which would resemble the original plasma. There would be nothing distinctively edge-like to find. We would arrive at a perfectly ordinary patch of cosmos that looks just like our own. The reachable edge, the cosmic event horizon, is even less of a place. It is a property of the cosmic acceleration. Traveling toward it would not bring you closer to it. The horizon would continue to recede from you at the same rate as the cosmic expansion carries it away. The horizon is, in this sense, fundamentally inaccessible. You cannot drive to a horizon. The light edge, the particle horizon, is similar. Traveling outward in any direction, you would, on average, move toward galaxies that you currently see at high redshift. But by the time you reach them, the cosmic time would have advanced, and your new local cosmos would have its own particle horizon, further from where you started. The horizon would move with you. What it amounts to is that the edges of the universe are not destinations. They are observational limits. They cannot be visited any more than the past can be visited. They are, in this sense, more like properties of our viewing position than features of cosmic geography. Now let's begin with the fifth misconception. The fifth misconception is that the cosmic edge tells us something specific about the cosmic origin. People sometimes assume that, if we could just look further out toward the edge, we would see the beginning of the universe directly as a wall of glowing light or a point of singularity in the distance. The correction is that we already do see the earliest observable moment of the cosmos in the CMB. The CMB is the surface of last scattering, the boundary between the opaque early plasma and the transparent post-recombination cosmos. Beyond it in time, the cosmos is fundamentally non-luminous. There is no further wall of light to see. The earliest moment we can observe in light is already in front of us in every direction, as the cosmic microwave background. The cosmic singularity, if it existed, would have been the moment of cosmic origin itself before any of the structure we can observe. We cannot see the singularity. We may not even be able to define it precisely, because the moment of cosmic origin is exactly where the standard model of cosmology breaks down. The earliest moment in cosmic history that we can describe with confidence is some fraction of a second after the singularity, and even that early description depends on theoretical models that have not yet been directly tested. No one expects, on first thinking about cosmic origins, that the singularity itself would be permanently unobservable. No one predicts that the earliest moment of cosmic history would be hidden from us not by distance but by the breakdown of our physical theories. The intuition does not anticipate that the cosmic origin is, in a precise sense, beyond the reach of any current observational instrument. We see back to 380,000 years after the Big Bang. We do not see and cannot currently observe anything earlier in light. The fifth misconception is therefore the most subtle of the five. The cosmic edge does not show us the cosmic origin. The cosmic edge shows us the earliest moment of cosmic history that was transparent to light. The cosmic origin remains for the foreseeable future beyond the visible edge in the era of the opaque plasma. It is hidden not by distance but by the basic physics of the early universe. Hold the image. 5 misconceptions. Each one is reasonable, each one is wrong. Together, they point at a deeper truth about what we mean when we say the universe has an edge. The edge is not a place. The edge is not a wall. The edge is not an exit. The edge is the limit of what we are allowed to see, and what we are allowed to see is, by every available measure, a remarkable amount, more than enough to keep cosmologists busy for centuries. On reflection, getting these misconceptions right is part of what makes the question we asked at the start of the night a serious question. The edge is real. The edge is measurable. The edge has properties that we can study, but the edge is not what the simplest intuition suggests. The edge is a richer, stranger, more interesting object than any of the popular images would lead you to expect. For the rest of the night, let the 5 edges sit gently in the back of your mind. Imagine the cosmos drawn as a set of nested spheres around you. At the center, the small lit room where you are listening. Around you, a few feet of warm air, then walls, then the world outside, then the atmosphere, then the dark space above. Beyond Earth, the sun and the planets of our system. Beyond the solar system, the nearest stars. Beyond them, the spiral of the Milky Way. Beyond the Milky Way, the local group, the Virgo cluster, the Laniakea supercluster. Beyond them, the cosmic web, threading outward in every direction. Beyond the cosmic web, the most distant galaxies JWST has detected, observed as they were within a few 100 million years of the Big Bang. Beyond those, the cosmic dawn era, when the first stars lit. Beyond cosmic dawn, the dark ages. Beyond the dark ages, the surface of last scattering, the visible edge, the CMB. And then, in every direction, the other edges, the light edge, the particle horizon, beyond which we have not yet been able to see, the reachable edge, the event horizon, beyond which we will never be able to communicate, the theoretical edge, beyond which our physics runs out and only mathematics ventures. The four further edges are not arranged on a map. They are properties of where we sit in cosmic time and what we can know from this position. Picture the camera in your imagination drifting outward through all of this, past the room, past the world, past the solar system, past the galaxy, past the cosmic web, past the cosmic dawn. The camera arrives at the CMB and finds it not as a place but as a sphere of light surrounding the cosmos, a flash from a single moment in cosmic history, frozen and propagating outward and never quite arriving anywhere because there is always more cosmos for it to traverse. The camera tries to push past it and finds that there is nothing earlier to see in light. Behind the CMB, in time, lies the opaque plasma, and nothing reaches us from that era except through the indirect effects of its physics on the cosmic patterns we measure today. The camera turns sideways and tries to push past the particle horizon into the cosmos we have not yet been allowed to observe. It cannot. The geometry does not permit it. The cosmos out there is real and probably similar in character to the cosmos we know, but no instrument we possess can resolve any of it. The camera floats, unable to cross. The camera tries to push past the event horizon into the regions of the cosmos we will never be able to reach with any signal we send. It cannot. The expansion of the cosmos has carried those regions beyond our future light cone forever. The camera floats again, unable to cross. The camera turns inward and tries to push past the theoretical edge into the inflationary multiverse, or the previous cyclic cosmos, or the higher dimensional structure that may underlie our spacetime. It cannot. The theories are not yet detailed enough to render. The mathematics has things to say, but not pictures. Let the camera rest. It has reached all four of the further edges of our cosmic knowledge. Beyond them, the cosmos may continue indefinitely, may contain other bubble universes, may loop back to previous cycles, may extend through dimensions we cannot perceive, we do not know. We may eventually know more, we may not. Slowly, the camera turns around and begins the long drift back toward the small lit room where you are listening. It passes back through the theoretical edge. It passes back through the event horizon. It passes back through the particle horizon. It passes back through the CMB. It crosses the cosmic dawn. It threads back through the dark ages. It enters the era of the first galaxies. It approaches our own galaxy, then our solar system, then Earth, then the building, then the room. It rests at the foot of the bed. The cosmos has, for the last few hours, taken up residence in your mind. The five edges are now part of how you know the universe. The CMB is the soft glow at the visible edge. The event horizon is the slow loss of distant galaxies. The particle horizon is the boundary of what light has had time to bring us. The cosmic dawn is the chemical transition between an empty cosmos and a structured one. The theoretical edge is the frontier of physics, the place where the next century of work will be done. What this means is that the question we started with has an answer in 5 different ways, and each answer is honest. The edge of the universe is made of light. The edge of the universe is made of expansion. The edge of the universe is made of darkness. The edge of the universe is made of the first stars. The edge of the universe is made of theoretical inference into regions we may never directly see. All 5 answers are true. All 5 edges exist. The cosmos has many boundaries. Depending on what kind of boundary you mean, there is no need to hold all of this. The cosmos will keep its shape whether you remember the details or not. The 5 edges are present in the geometry of the universe, whether you can articulate them or not. The point of the night was not to memorize the facts. The point of the night was to walk along the boundary of what we know, gently with no rush, and to feel the shape of what lies just beyond. If your eyes are closed by now, that is fine. The story has done its work. The cosmos is in the room with you, in the slow, steady form it takes during these long, contemplative hours. The room is warm, the night is here. The 5 edges are in their places. There is nothing left to do tonight except let the picture settle and the breathing slow. Sleep well tonight, and tomorrow we will continue to explore the deepest mysteries of the cosmos together.